So what we'll be doing now in chapter 13 is we're going to be combining what we learned about kinematics and Newton's laws. Okay, so we're going to be talking about forces and accelerations. Okay, that's how that works. So one of the things you need to keep in mind as we move into this material is that Newton's second law is really like a bridge. Okay, so here we have Newton's second law, like this. Okay, on one side we have kinematics, and on the other side we have everything we know about forces. Okay, and so Newton's law works between those two. All right, and so a lot of times, or most of the time, what we're going to end up doing is maybe we're given information about what are the forces in a certain situation, and then we've got to figure out something kinematically. Okay, for example, such and such a force is acting on a particle. How fast is it going after it's moved 10 meters? Okay, or what's its acceleration after 10 seconds? Or how far has it gone? All that kind of thing. Okay, so that's one category. All right, so we're given forces. We have to find kinematic stuff. And then we can go backwards on that too. We could be given kinematics information and we're being asked to find something about force. All right, now this particular example is that category there. Okay, so let's dig into it. The motor winds in the cable with a constant acceleration such that the 20-gram cable moves a certain distance in 3 seconds starting from rest. Determine the tension developed in the cable. Okay, then there's another detail there. Okay, so what's the thing we're hunting for? Determine the tension. Okay, and what's the thing that we're given? Moves a distance such and such a distance starting from rest. Okay, so it's giving us information about its motion. We're supposed to find out what the tension is. Okay, and so what we're going to do in order to do this first is just kind of look at the thing, and let's go ahead and get our forces laid out. What's at work here in this situation. And so we have our, whoops, that is not the right thing. We have our tension here, of course, from the cable, T, and that's the thing that we're looking for. All right. Now, remember, okay, also as we get going on this, remember that a diagram and a free body diagram are all going to be very important. So sketch the scenario, make your free body diagram. All right, so we don't have to sketch the scenario because I have it here. If I were doing this on my own, I would do something like this. Okay, I'd say, okay, the box is here. All right, it's getting pulled. And then sometime later, it's up here. Okay, and I know this distance is S, and I know that that amount of time is 3. All right, so that's how I do it on mine. And in fact, you probably can't see it there, but that is exactly how I did it on mine. Okay, so let me erase this stuff here. There we go, and we'll get on with it. Okay, we have the weight, of course, here. And we've got some friction operating. And we've got a normal force acting on our crate like so. So that's what we got for our forces. Okay, now let's go ahead and put those into a free body diagram. And I'm going to change pen colors real quick. Okay, now when you have a tilted scenario, when you're on a plane, it's often helpful to tilt your free body diagram axes. Okay, and now you can see everything lines up really nice. Here's my tension. We don't know that. Here's my friction. Okay, and normal force goes here, and then my weight goes here. All right, now that of course is mg. Now what I usually do, instead of putting my weight vector on there like that, is I find that it's very convenient to go ahead and break it into its components. So we have the perpendicular component and we have the parallel component. Oh, and by the way, that's our friction. Okay. Now, again, I've said this quite a few times, but one of the things, I'm not real big on just flat out memorizing lots of stuff, but you just need to flat out know that the perpendicular component is always going to be mg cosine theta, and the parallel component is always going to be mg sine theta. Okay, as long as you're given this angle down here for theta. Okay, that's how it's going to be. Okay, so there we go. Alrighty, now let's keep rolling with stuff here. And what we're going to do is we're going to look at the forces in the y direction and the forces in the x direction. Okay, so let me start up here. Okay, so there's Newton's second law. Okay, and so what we're going to have then is my normal force is up. The perpendicular component of the weight is down. And there is no acceleration in the y direction. All right, so that's equal to 0, which tells me that my normal force is that perpendicular component, mg cosine theta. Okay. All right, now what I'm going to do is let's take a look at what's happening horizontally. Okay, just like this. And horizontally, we've got tension minus the friction minus the parallel component of the weight. And that is going to be equal to ma, because it is accelerating up the incline, just like that. And that a is what we're looking at. Okay, so let's take that one more step. Let's just flesh that out just a little bit more. All right, we are actually solving for the tension, so I'm going to go ahead and do a little bit of algebra here. Whoops. Okay, plus the friction plus here. Okay, so I've got ma plus, now my friction is mu times the normal force, okay? But what we found above is that normal force is mg cosine theta, okay? So I used that term up there. And then my parallel component for my weight is mg sine theta, okay? Just like so. Okay, now I want to do one more step of algebra here, just so it looks a little bit prettier. Okay, because I've got the mg term is common like this, so we can say this is mu cosine theta plus sine theta. Okay. All right, now the only problem is I've got two unknowns. We don't know t, we don't know a. Okay, so that's where this bridge aspect comes in, okay? Because we can get the acceleration. Remember, way over here, it tells us moves a certain distance in a certain amount of time. That's kinematics, so that's where we're going to get our A from, okay? And we're going to assume this is the tension is constant, which means we'll have a constant acceleration situation. And that means we get to use Sam, Bumblebee, Optimus Prime. We can use all those relationships. And so here we're given a distance and we're given a time. And so this is a good one for Optimus Prime. Okay, and so we're going to come in here and we're going to say delta S is V initial delta T plus 1/2 a delta T squared. Now we're starting from rest, so we throw that term out. We're looking for the acceleration, so we're going to have A, and we'll have 2 delta S over our delta T squared. Okay, plug in some numbers here. 2 and our distance is 6 meters. And our time is 3 seconds. Okay, so if we look at our units real quick, you can see we're going to end up with meters per second squared. This is actually a squared term here. Okay, and A then turns out to be 1.3333333. Okay, now I've left an extra digit on there because this isn't my final answer, and so I want to carry more digits with me while I'm doing my computations. All right, and then all we're going to do is we're going to take this guy and poke it in right there. Okay, then we know everything else. We know the mass, we know mu, it's given to us, we know the angle, boom, boom, boom. All right, we just plug it into our calculator and we're good to go. Okay, so you guys all have competent calculator skills, so I'm going to leave that to you. Okay, and get ready for the next one.